Alrighty, so I entitled this Better Living Through Chemical Oceanography. I was just talking with David Taylor. I think you were saying one of your sons is a chemical engineer. My father was a chemical engineer. A chemical oceanographer is very much like a chemical engineer, except instead of making lots of money studying oil or water movements on land, we work in the ocean. And hopefully, oops, there we go. So I'm going to start with, we're going to go all over the globe, both mentally and intellectually. One of the things I was going to start with is, what is a scientist? And I took two or three other talks that I've given around the country. One is about being a female scientist. One of them is about working in the field. And another one is about pollution and things like radionuclides. So thank you. So when we all were growing up a long time ago, or everybody but Phoebe and a few other people in the room, when we thought of a scientist, we thought of a man, typically. We thought of a man with crazy hair, typically like Einstein. Einstein was our version of a scientist. And when we asked kids to draw a scientist between 1966 and 1977, out of 5,000 kids, almost all of them would draw a male scientist and not a female scientist. In fact, only about 20 or 30 kids would draw a female scientist, and those were all women that drew female scientists. And that was the same whether you asked young kids, teachers, or high school students. Everyone thought this is how you had to look to be a scientist. And I'm here to tell you, I don't look like that, and I am a scientist. So. But my father didn't have the crazy hair, but he was a chemical engineer. He did work for NASA and for Phillips Petroleum, and he totally did fit the whole white shirt, thin black tie, standing in front of a big blackboard doing equations. So that was what people saw. This is reinforced by famous scientists, both imaginary ones and real ones. When we think of scientists, folks like the Reverend Jim there would be one of the people you'd think of, or Linus Pauling, or Einstein, or Galileo. Thankfully, this stereotype is dissolving. And now when we talk to kids about who can be a scientist and what does a scientist look like, now from 1960 to 2013, the percentage of women holding jobs in science increased, and the number of kids that were drawing only male scientists decreased. So kids started drawing scientists that look like normal people. There's all kinds of great things online as far as selfie scientists. So I advise you to go online and look up and find your favorite scientists. And we have tattoos, we're all races, we're all sizes. We come from all over the world, and that's what a real scientist is. So one of the things I've done most of my life is try to demystify science so that people don't think that it's something for someone else, that it's something for everyone. Everyone can be a scientist. Everyone in this room is a scientist. Anytime you go outside and look at something and go, I wonder what that is. Why is that growing this way? Why is that wet? Why is that tall? What does that smell? You're being a scientist. You're asking questions of the natural world. And at the bottom of this, I put a fun fact. I see most of us do not wear lab coats. That's kind of an old-fashioned thing. Cotton lab coats actually are a dangerous thing to wear in the lab. So that's more of a medical doctor thing and not a scientist thing. So why did I become a scientist? Well, part of it is because my father was a scientist, and so I had that modeled at home. But he passed away when I was 9, so that went away fairly early. I actually wanted to be an astronaut. This is, during the late 60s, early 70s. Being an astronaut was super exciting. But unfortunately, I could not be an astronaut for 3 different reasons. 1, I was a female. 2, I don't have 20/20 vision. Back then, to be an astronaut, you had to be in the Air Force, and you had to have 20/20 vision. You couldn't have any kind of corrective lenses to be in the Air Force and be an astronaut. And the third thing was you had to be in the Air Force and be in a hierarchy and be willing to put up with military command, which was not my cup of tea. So I had to pivot, and I started going to school, junior college at Tulsa Junior College, and I took a class in oceanography from an out-of-work oil, someone that was a chemical oceanographer and chemical engineer who was out of work because of the oil bust. And a lot of people won't remember this, but in the early 80s, the bottom fell out of the oil market, and hundreds of thousands of people lost their jobs all over the United States. So this person who was doing oil exploration came and talked in my community college class and told me about oceanography. And once I learned about the fact that the poles, the North and South poles, have been flip-flopping over the last billions of years. So when you look at the seafloor, which grows out from these giant volcanoes at the seafloor rift, new seafloor is made and it extends like this. And you can see in those iron parts of the seafloor, the magnetic pole going from north to south, north to south. Now, none of us are going to live 50,000 or 100,000 years, so we don't see this with our own eyes, but we can measure this on the seafloor. That actually blew my mind. The fact that something so intrinsic to the natural world could be 180 degrees off. I'm like, I'm in. I definitely want to study this. At that time, we only knew 5% of anything about the ocean. We knew in the 90s and 2000s more about the moon and space than we know about our own ocean. Just swimming out here, looking underwater, there's less known about that than places far away. Now we're up to about 15 or 20%, but it's still an unexamined frontier. It's still an exciting place to go and be a discoverer. There are 4 branches of oceanography. So how many people in here, when I say name an oceanographer, who would you name? Cousteau. Everyone will name Cousteau. Cousteau is a filmmaker and an inventor and not an oceanographer, but did more for oceanography than many, many oceanographers. But most people will name Cousteau. They might name Sylvia Earle, who's a diver and a marine biologist, but you usually think of a marine biologist. When you think of an oceanographer, you think of dolphin hugging, maybe fishing. You think of all the creatures living in the ocean. You don't think about the water of the ocean, the waves, or the sediments. And there are oceanographers that study all those other things. So you've got marine biologists that are biological oceanographers, and they're studying everything alive in the ocean. You have a chemical oceanographer, which is myself. We study all the chemistry of the ocean. So to me, a whale is cool, but it's actually a really large particle moving through the water that I have to worry about how it's interacting with all the carbon. I'm not really thinking about it biologically. I'm thinking of it in a particular form. Geo-oceanographers, those are ones that make the most money. They're often studying things like oil formations and the geology of the seafloor. A coastal oceanographer, someone that's studying about all these storms, would typically be a geo-oceanographer, a geological oceanographer, someone who is knowledgeable about what happens with sediment and with rocks and with sand. And then a physical oceanographer is studying all the physics. So all of these oceanographers all have to understand physics. Heat, cold, how currents move, how waves are created, what happens with weather. That's all physical oceanography. And you can see all of these branches here and how they expand and how they're connected. I put paleoceanography all at the very top all by itself with a couple of little fossils. That is becoming a really big part of oceanography. And some people feel like it should have its own category. Because to be a paleoceanographer, you've got to learn all of these things, but do it millions of years ago. So you've got to be able to interpret all of this from a long time ago. This is a very complicated map drawing, and it's complicated for a reason. Let's see if this thing still works. Yep. So make sure I don't blind everyone. Phoebe talk trick, never blind anyone with a laser. And oh, since it's a TV, oh, you can almost see it. See, it's not. That's a cool trick. So it's going away. So this is why a good speaker always has an actual physical thing to tap the screen with. But I can also do it a little bit with my cursor.
Guy with the lab coat.
Yeah, he probably would have. Well, technically, can you? Yeah, you can see my little cursor there. You getting dizzy? Okay. So all this thing is doing is showing you all the different things that are occurring in the ocean. So when I look at the ocean, I'm thinking about phytoplankton. I'm thinking about the primary predators. I'm thinking about lots of people study poop now. They study whale poop, phytoplankton poop, fish poop, because that's a huge source of carbon as it sinks to the seafloor. But you can see all of these different interactions. You've got changes between the upper level ocean and the lower ocean. When we talk about the pelagic zone, we're typically talking about the main part of the ocean. You've got the very top part is the surface. This is where all of the sea air exchanges are happening. This is where all of the issues with carbon dioxide. So carbon dioxide is getting injected into the surface of the ocean. It's being used up by phytoplankton. Those phytoplankton are blooming. They then die. They transport their carbon. down to the sea floor. As they go down, bacteria scavenge them and decompose the phytoplankton. It all gets buried, and in some cases is subducted under giant subduction zones. But all of they're specialists for every single process that you see here. Everything you see has someone doing something related to that. So there's many specialties in chemical oceanography. You might study atmospheric science, carbon fluxes, you might trace nutrients. Nutrient tracing is very important because we've got nitrogen and phosphate coming from fertilizers, from septic systems, from the sky. We trace this all around the planet because anytime it shows up in excess, we get things like harmful algal blooms. We'll get too much fertilizer in areas. We'll get dead zones. The whole Gulf of Mexico has a giant dead zone because of too many nutrients coming off the Mississippi River. So nutrient studies are incredibly important. You can study organic chemistry, oil-related chemistry, ocean acidification you've heard a lot about. And then you look at your applications. How do you use this information to learn more about our planet and especially what's happening with carbon and what's happening with climate change? And we frequently look at things like pollution pathways. So in my next few slides, we'll talk about some major pollution pathways. So I try to get people to think about where they've been on the planet, where they've been near, and how could I, as a scientist, track that on you? And then think of yourself as the ocean, and that's what I do. I basically look at the ocean, look at what's inside the ocean, and use my knowledge of where it's been, what it's interacted with to figure out why it looks the way it does. We also use something called a box model, and this is where other scientists get mad at us. So we take the whole ocean as one big box, and we take inputs into that box and inputs down into the sediment, and then we make decisions based on this giant box. It's another complicated map showing all these sinking particles. One of the biggest ways to remove carbon from the atmosphere is actually these sinking particles, and all of these exchanges that are happening with the atmosphere with nitrogen, carbon dioxide, dimethyl sulfide. So let's say you have a paralytic shellfish poisoning issue on the East Coast or on the Lower East Coast near Maryland. You have shellfish that are releasing DMS, diamoic sulfide, which is a problem for people with asthma. It's something that actually can cause paralytic shellfish poisoning. We can measure that with instruments and tell you where it's going and how far it's gone. So most chemical oceanographers actually call ourselves biogeochemists. So I have to know a little bit about biology, a little bit about geology, and a little bit about chemistry to do my job. And a lot of what we do is tracing contamination, whether it is coming from industry, farms, pig growing out facilities, giant parking lots, aircraft, from the ocean, shipping lanes, plastics that are traveling around the world. So everywhere in the world now, you can measure rodeo, you can measure Roundup. All of us have microplastics inside us, in our blood. We all have everything we've created. Now, when we were kids, we all had lead in our blood from paint and from leaded gas. That is the one thing, two things that we've done perfectly well is we've gotten rid of lead in almost every human being, excess lead. And now we don't have to worry about huge IQ drops in our children because we made huge changes in laws that removed leaded paint. Can't buy a house now without proving that there's no leaded paint in there. We got rid of leaded gasoline. And if I take a sediment core, I can see those two. I can see that in the core. When I take a big, if I go out here in a boat and take a core, I can see the years that leaded gas went away and leaded paint went away. That's how big a change we made throughout the entire planet just from one action. The other thing we fixed is CFCs. I know you get annoyed if you go to get rid of an air conditioner and it's got Freon in it and it costs like $6 million to dispose of this air conditioner because someone has to actually use a device that extracts the carbon fluorocarbons out of it. That was killing the ozone layer, completely causing huge problems, a huge amount of cancer, skin cancers by letting too much solar rays in. We changed that. We made hairspray illegal. We made all of the accelerants illegal that are linked to CFCs. Those break down in the atmosphere. And so you can see that in the sediment core. You can see that in our blood. You can see it in our kids' hair. If I took a clipping of kids' hair, I'm not going to find those contaminants. which I'm really proud of. And we do that for a lot of things. We're doing that now for PFAS. You guys have heard about PFAS, BPAs. Just a few years ago, biphenyl acetate was inside all of our drinking water bottles. It was something that was designed because it helped a lot of things, just like Teflon helped a lot of things. But unfortunately, when things are really helpful, sometimes they have properties that then get into our systems, and then like Teflon doesn't react with anything. So it's almost impossible to remove Teflon because it won't attach to anything. So our, progressive things have introduced a lot of things, and fortunately we were smart enough to have taken care of many of these things. But we still live in a contaminated planet. So once again, going back to the hair example, I could take a sample of hair from each of you all and say, approximately maybe where you lived in the United States, how close to a major city, how close to freshwater sources versus salt sources, how close you might have lived to a farm. If you had a lot of idling diesel machinery near me, all of those would be recorded in both in your hair and in your blood. So I have a copy of this over here. Our Bible for chemical oceanographers is called Tracers in the Sea. And so we use different events, like I'll talk about the World Trade Center. I'll talk a little bit about 3 Mile Island, Fukushima. We use these big disasters, create big indicators in our natural world, just like the KT boundary and the giant meteorite that killed all the dinosaurs. You can find that in any kind of ancient stone system. You can find that big break where all the dinosaurs went away. You'll have that extinction layer. We can find evidence of things like 3 Mile Island, bomb fallout from the 60s, Fukushima, fortunately not so much, and other things, which I'll talk about in a second. Oh. So quickly, this is the research I did as an undergrad. I studied trace metals. So I studied all about metals in fish and in rivers and bays. When I went on to grad school, I studied radioactive iodine. So I'll talk a little bit about radioactive iodine, and I used it to trace processes around the world. And then when in my postdoc era, I studied the World Trade Center. So I studied the ash from the World Trade Center and what it did in the Hudson River and was able to track it. And then when I was on Nantucket for about 12, 13 years, I studied coastal erosion, water quality, and marine policy. And I helped do a couple of papers that looked at iodine 131 as a tracker of wastewater coming from sewer systems. So pictures of me from long ago, 30 years ago, putting a lot of oceanographic equipment overboard. So oceanographers, when we go out on a ship, we're on a ship for 2 weeks, sometimes 4 weeks, with 30 of our closest friends, living just like fishermen live every day. And we're putting these this is called a rosette with niskins. And we lower those through the water column, and it opens and closes at each depth. So they're controlled by a computer, and it'll go down 2 miles. I mean, the ocean's very deep. And as it goes down every 200 or 300 meters, it'll close and seal the water at that depth. So we'll send it all the way down and bring it all the way back. And we'll take gulps of water that are protected. It comes down, it's ice cold because the ocean is ice cold down at deep. And so that's how we collect water a mile down, 2,000 meters, is using these. This thing on the right there is called a benthic lander. This is very similar to what you would use on the moon. It actually goes all the way to the seafloor. It opens up and it measures pH on the seafloor. And then you use a trigger because you don't have a line going all the way down to the seafloor. So you have to use a trigger that releases weights and then pops up to the top of the ocean, if all goes well. And these things, gosh, 30 years ago, that was $300,000, $400,000. So if you lost it, you were in trouble. These are probably only about $20,000. But the water in them is worth each day each container is probably worth about $5,000 because of the time it takes to collect it. So when I go out on a research cruise, I've got 2 weeks to get 4 years worth of data. Everything that I need, I have to get then. There's no being seasick. There's no, I don't feel like doing it. There's no 24 hours. You're collecting water the whole time. And you're sharing that water with maybe 40 other scientists. So, and you're also mapping the ocean as you're doing it, so you know exactly where you are in space and time. So you can't go back in time and collect that water again. So if I want to record how much rodeo is building or glyphosate is building up in the ocean, I need those years worth of data to show how anything's building up or going away in the ocean. So you can't recreate that time. When I was quite young and doing trace metal work, we did what we were trying to do is make everything super, super clean. So we're measuring things at very, very small volumes and very, very clean. And the whole room was Teflon. One pencil would contaminate the whole room for lead. I had to wear all plastic all over me. You couldn't have like shampoo for dandruff because there's zinc in that. You can wear certain types of deodorants, everything we're shedding as we walk around. It's kind of disgusting maybe, but if I was measuring trace metals, you wouldn't be in this room with me. You know, we would have like those big computer rooms where you come in and there's Teflon and everyone's wearing the Tyvek coats. So we did versions of that 30 years ago and found some of the lowest numbers in Galveston Bay, and a very polluted bay near the Texas ship channel. Why this was important is they were changing laws because they thought it was polluted. So they were making industries do things they didn't have to do quite yet because the numbers they were measuring were higher than they really were. So their boat was contaminated. And for instance, if I had to do trace metal research, I would get in a Zodiac and I would go a mile away from the boat. I would go upwind, upstream, and collect things where nothing is coming off of me or the vessel to collect the water, to test it, let's say for lead. If I didn't do that, if I turned around and I had my diesel engines, I mean, you're testing your own engines. So there's a whole variety of things that we did to make sure we could find what is the real level. And that happened across the entire United States, and all the numbers across the United States actually came down a couple of orders of magnitude because of doing things cleanly. Not that anal now, and don't come to my house and say, hey, I thought you could do things really cleanly, because I do not reflect that in my own personal house. This is a long list of stuff, and I'm just showing you this because to be a chemical oceanographer, you got to learn how to use a bunch of different instruments to measure all kinds of different things. You have to have a lot of field techniques, and you have to have the ability to do a lot of field work. So it's standing out in the middle of nowhere or out on a boat with $100 machines, $1 million machines, collecting water, sediment, fish, soil, phytoplankton, all kinds of things. Something as simple as, you know, $100 phytoplankton bag to 300,000 or 400,000 benthic lander. In graduate school, I went and stood around in other giant rivers around the country, and I measured trace metals, mercury in China. I looked at transport of carbon using iodine, and I did large-scale sediment movement in the Mississippi River. So I'd go to areas south of the Mississippi River and go offshore, and I would collect sediments to tell me about rainfall. So radioactive iodine is one of the things I studied the most. Iodine is biophilic. There's 3 different isotopes of iodine. There's stable iodine, which is just regular iodine. There is 129 iodine, which has a half-life of 16 million years. I'll tell you a little bit about that. And then there's iodine 131. So if you go to the hospital, I hope you never do this, but if you do, you have thyroid cancer, they will flood your thyroids with this radioactive iodine to basically knock your thyroid into submission. So then if you go home and use the bathroom, which hopefully everyone does, that iodine gets into the wastewater and gets out into the harbor. That can actually be measured in Boston Harbor, New York Harbor, Brazil, San Francisco Harbor, Seattle, most of the major harbors in the world, because that many people are getting thyroid treatments, and that many people are actually having their cats treated for thyroid cancer. So it's not just us, it's also our pets. Don't panic. Iodine 131 is not dangerous. What it is short-lived. It only sticks around for 8 days. In 40 days, you can't find it at all. So it's an indicator of very recent organic matter from sewers. Now, why would we care? Well, stuff does come from sewers that is dangerous, not iodine, but things like testosterone, ibuprofen, epileptic seizure medicine. Everything we put in our body, 20 to 80% is retained in our body. 20 to 80% goes away in our waste and goes into all of our harbors. In some cases, fish, frogs, this is the problem with frogs, all kinds of creatures are swimming around this water, you know, breathing the air. They're going to absorb all these chemicals in their system. This is why there's a huge situation around the world where a lot of fish, for instance, are not, the sexes are not lining up. They're having more female fish, more female frogs, not enough male frogs. We're having endocrine disruptive behavior, and we're ending up with the wrong sex for different creatures. We're even starting to see this in plants, which is interesting. So iodine, going back to tracers in the sea, I use radioactive iodine, which comes from radioactive fallout, from nuclear power plants, and from hospitals, and from the sky. Those are the only four sources. So if I have a sample, I know that in that sample, one of those four things was involved. Iodine is biophilic. It loves carbon. It loves seaweed. If you go out and get seaweed, that's your biggest source of iodine right now. If we all wanted to have a lot of iodine, we just go and grab some kelp. It attaches to carbon, and it is different whether it's terrestrial or in the marine world. So I used it to track carbon around the planet because iodine is very common in the ocean. It's very rare in terrestrial or on land. And so I could look at the ratio of these two things to tell exactly where it was. It actually works, the radioactive iodine 131 works really well for tracking lobsters, for instance. You can see how close they are feeding to a stormwater outfall in larger areas where there's hospitals. This is going to be too deep, so I'm going to pass this. A lot of science, a lot more science. This is just illustrating the multi-tracer. This is using radioactive plutonium. This peak right here is 1963. What happened around 1963? It's a big movie that just won an Oscar all about it. Yeah, so this peak is all of the bomb testing that America did in the Manhattan Project in Nevada and Bikini Atoll. And that can be recorded in every bit of sediment anywhere in the world. You can see this big giant peak. This is a radionuclide, plutonium. It wouldn't be there normally unless there was something like Indian Point or someplace that was leaking a radiation. And we can find that peak and use that to date the sediment. So that's what radio dating is all about. It's using a known event, something weird. I can tell you that's 1963. I can then tell you how quickly that sediment is accumulating. Now, why is it important? I can tell how much land is coming off the entire United States into the Mississippi River, how many particles are actually coming down the Mississippi River based on things like this. You can look at drought, rainfall, soil erosion, all based on something that simple. Tells you a big story with one point. I'm going to jump ahead to the World Trade Center. So as a scientist, this is a little ghoulish, but when we see something horrible happen, we're like, I wonder what's happening with that material. And so you can actually still see that picture's not that fuzzy. That's still all of the ash in the air. This is 3 weeks after the World Trade Center, which the buildings should have been behind us and are no longer there. So we got a overnight, this is my student who's now a professor at the U.S. Naval Academy, incredible student, Joe Smith. We got emergency funding to jump in a vehicle and go down and collect ash at the World Trade Center and sediment in the Hudson River. And the reason we got funding almost immediately is because we were worried then about where dirty bombs might go in the Hudson River Bay. So there's Staten Island, there's the Statue of Liberty, there's all of these bays that were just recovering, just getting clams back, just getting blue mussels back. And then, America had to wonder if someone comes and releases a dirty bomb, where's that material going? Where are you going to dredge it? And so we jumped into the car. One of the longest days of my life, I drove from Boston to New York, got into a vessel that we had to row. They weren't allowing no motorized vessels. This is 3 weeks. I mean, the security was unbelievable. I mean, we had like 12 different security checkpoints. Jump into Row the Apple, which, by the way, if you're ever in New York City, you can actually get a free rowboat at Row the Apple. Rowed out, put a little sediment core down into the Hudson River, collected very gently the sediment sample, brought it up, canned it into tuna cans, looked like cat food cans, actually canned the sections on the dock right there, threw them in the car, drove all the way, still the same day, drove all the way back to Boston and put them on a gamma counter. Because we did everything in 24 hours, we were able to find radioactive iodine 131. No one else in the world up to this date had found it anywhere. They just hadn't processed that quickly. If you go right now and take a water sample and you go put it in your fridge, and then let's say you take it to the lab next Friday, by the time you look at it, everything's gone. This is me many years ago, not that many, maybe 20 years ago, putting this as a gamma counter. This is about 8 inches of steel and copper. This is all shielded from all external radiation. So I only want to know what's the radiation in that can. I don't want to know any other radiation. So this whole thing weighs 2 to 3,000 pounds. Once it's placed there, it can never be moved, and it's completely shielded to look at natural radiation. And obviously, I'm happy to do it. So we took this material and we went to 3 different places: MIT, a place in Menlo Park, California, and there at UMass Boston. And what we did is and I brought copies of this paper, we mapped the particles in the ash and the particles in the sediment. So you wanted to see exactly where the ash went in the entire harbor. So this is the ash at the top. We were looking for asbestos, we were looking for radon, we were looking for radium. We were looking for a lot of things. We were really worried about things like fiberglass and silica, which we found. We did not find, thankfully, any asbestos. We were looking for these exit signs, those all have radiation. So we were looking to see if we could actually detect exit signs. Computers have lithium. We were looking for all kinds of things. We mainly found melted zinc and copper balls, iron balls. You could actually see how these particles have been melted and ejected, and tons of drywall, gypsum. We could actually tell you what company made the gypsum. So all calcium, strontium, all gypsum. And the bad thing is, see how long and skinny those particles are? That's inhalable. That's basically fiberglass. So we found a lot of fiberglass, and we were one of the first groups to talk about World Trade Center cough. Because since that's inhalable and it's fiberglass, you know, if anyone's ever done fiberglass work, you don't want to breathe that, right? So the whole city of New York had to breathe gypsum and fiberglass. And we knew that that would get lodged in their esophagus and they would start having cancer, which they now have. So these bottom ones are those same particles in the Hudson River. So we were able to find these very specific particles that wouldn't naturally be in the Hudson River sediments in the Hudson River. Totally changing gears, abrupt change, but I'm from the field station world. I've worked in a lot of different field stations. So I'm going to switch from some of my science and talk about things related to field stations, because we're here at a field station. I worked at Nantucket. This is a 100-acre field station that I helped run in a beautiful salt marsh. One of the things I did, a lot of people go, well, if you like science so much, why are you here? You know, this is an educational facility. Why aren't you at MIT or Menlo Park making $250,000 a year, or who knows what those be? It's because I love education. And I love working with kids. And I love telling kids. I've had many conversations with kids about things like radionuclides. And I've had many 3 a.m. horseshoe crab counts with kids. Or up there, we're going to actually build this for our classes this year. We're going to have 2 of these beach profiling sticks so we can go down to Drift Inn and actually measure the change in elevation. You can just stand there and probably measure it, but we'll measure the change down to a millimeter of what's happening in our coastal areas. Seining, going out and seeing what creatures are living out there. I had no staff on Nantucket, so I had an army of high school students that did all of our water quality work. They would put these settling plates down and collect different types of algae so they could see how tunicates and different sea squirts are moving in. Very common research, very simple to do. Very scary because like 40% of what you're seeing there is invasive. Easy to do, exciting. A lot of water quality research. This is all looking at nutrients like nitrate and phosphate, the 2 biggest problems on Nantucket, multi-million-dollar island, people who are basically drinking their own fertilizer and septic because it's nothing but sand. And the groundwater is only 6 feet on average down. So where do you put your septic leach field? You know, try explaining that to someone who spent $7 million buying a house. I worked with a lot of great kids that actually helped pass some laws. We were able to ban the use of phosphate on island and certain types of potassium and nitrate. So these kids actually got in front of 1,000 people at town meeting and talked about how quickly fertilizers got into the groundwater because they went out and did the science with me. So they collected the samples, they came back and measured it. There was nothing between them and the science. So they could speak their truth because they actually measured it. Got to work with Mark Ruffalo, who unfortunately did not win an Oscar last night, but I was rooting for him. So, and what they did say about him is true. He is one of the nicest people in the world. He came out to the Nantucket field station to work with me and to work with these kids to talk about ways to do water quality testing and remove that mysticism so that people anywhere could see what's in their water. Because it should be all of our rights to know what's in our water. And that's one thing I recommend to everyone. First thing we did when we got to Waldoboro's, we measured our water, and what was it full of? Uranium. So it affects your kidneys right away. And so $3,000 system later, we don't have any uranium or radon in our water. And it's because of the natural rock here in Maine. I mean, it's not because there's a secret military outpost here, but I would know if there was. In fact, that's one of the things I'm doing, been doing on the, is helping people like Senator Markey look at things like the Pilgrim decommissioning to make sure they're not spilling some of their wastewater, radionucleated wastewater into the Gulf of Maine.
Sarah, does Mark Ruffalo have any background that, or was he just interested in clean water and helping kids farm?
He has two, he doesn't have a scientific background, but he had two nonprofits, Water Defense and 100% Solutions, and he's super serious about it. So he really does a lot of the research. So I would listen to an EPA call with him in real time. So he would, be listening to something happening down in Congress, and I'd be on one phone and he'd be listening to a 4-hour, lecture very similar to this. While I'm interpreting for him, he'd go, why is that scientist saying this? I'm like, scientists have to be sure. That's why because it's frustrating to people who are advocates that scientists need to be 99.9% sure. It's unlikely for us to say things are happening until we know there's no other sources of contamination, for instance. And so that was frustrating to him. But no, he doesn't have a background, but I worked pro bono as his senior science advisor. So you'd have this team of advisors around the country, and he'd just call them up and go, I see a bunch of glyphosate. Can you tell me about it? Or fracking or things like that. I've worked at 3 other field stations, the Rocky Mountain Biolab in Gothic and Crested Butte. I worked at 5 different field stations in California. This is my Stebbins Coal Canyon, my beautiful 5,000 acre field station that burned completely to the ground. David, look at you. Okay. Partially natural, partially created by climate change. The big problem with this is the soil actually burned. And so then you get rainfall events and you're washing the soil into all the streams. And so you could really contaminate streams. And then right before I came here, I worked for the Center for Coastal Studies, who does a lot of work with right wells, with whales, with water quality, with gear, ghost gear, with sharks, a bunch of different things. So the last 2 things I want to tell you before I read a quick poem is why it's fun to be a scientist. Nice thing about being a scientist, there's no uniforms. I know that's a silly thing, but when I was a kid at Wendy's, I'm like, I don't ever want to wear a uniform again. So you can discover things no one has ever seen. You really can. Like the radioactive iodine 131. No one had, people knew existed, but people didn't know it was measurable in harbors. You can actually be an expert in something. So I'm not going to bore you, but I could talk for like another 2 hours about iodine, right? And I would be an expert, one of the top 30 or 40 in the world on iodine. So you can know something deep down that other people don't know. It's actually very collegial and creative to be a scientist, helps you to think creatively. You get to travel to beautiful places and stand in the mud for hours. I've been to every major river in the United States, from Sabine up to the Connecticut River, to do water quality testing for iodine. So I've seen the Suwannee, the Chapalaya, the James River, all these beautiful places. And you get a chance to connect with nature, because even though they show us in the lab a lot of times we're outside doing science, like my poor students were a couple of years ago on a salt marsh in February on Nantucket. And this is when it's not fun to be a scientist. If you tend to get seasick, being an oceanographer is not the best thing. But you can do it. You just got to be prepared. You're going to be eating a lot of pretzels. That's what you do on boat. As any fisherman knows, you're just, you out eat the sickness. It's long hours. If I'm out doing water quality work and it's 5 o'clock, I don't get to just go, drop my stuff and go to the car. You're still doing research. Animals and plants, they don't take any breaks. Computers die and they erase stuff like your thesis, a week before you're ready to defend. That's why you have multiple computers. You're not going to become rich. I don't know. There's not very many scientists that are super rich. Sometimes you feel like a real idiot. You know, you have to be dumb before you're smart. You're going to be presenting at a big meeting and someone smarter than you is going to be in the audience and they go, hey, that point is wrong. Or you're interpreting all of this wrong. And it'll be in front of all your peers worldwide. And they'll go, that's really blah, blah, blah. And you're like, oh, geez, it is. And thank you for pointing it out in front of my boss and every person I've ever met. It's not always 70 and sunny. Things like goggles and protective gear can be hot and sweaty and annoying. And when I do trace metal work, I can't wear bug spray. I can't wear perfume. I still don't really wear any of that stuff because it contaminates the sample. If you take a sample, if I put bug spray all over me and go out and take a water sample, A, I'm killing half the fish just collecting the sample, and B, you're measuring your own bug spray. So that's hard to explain to people. One of the things we're doing here is the virtual field. I'm not going to go into big detail about this, but this is something really fun that we're doing. We're providing all over the world with lots of partners, visits to field stations for free through videos around the world. So this is something I brought here. And then I just want to say thank you. This is one of my students drew this about 15 years ago. I have a whole case of all of the little things that they've drawn. And so I enjoyed doing this. And I'll read a quick poem and then take some questions. Does that sound good? Are you up for a poem? Is a poem all right? It's short, it's scientific. It's not really weepy. Okay, from my shortest book. My husband's here, he's a real poet. I'm a fake poet. Lenny is a very good poet. But this is my poem, and now that you've seen all of these, you'll be able to understand it a little better. So 20 liters, 20 liters, 20 liters. The water piles up in acid cleaned 20-liter high-density polyethylene jugs. Surrounded by seawater, we must bring our own double distilled, extremely pure fresh water, ion-free, water so pure it cannot conduct electricity. Hundreds of liters in total, queued up along the starboard side of our 123-foot vessel, the research vessel Pelican, named for the island we launched from, nestled in the lobe of Galveston Bay. Argon and nitrogen gas tanks roped tightly between pipes, giant benthic landers crowd the deck, ready to deploy. 100-meter long spider-legged nets to close upon their krill prey. Gangway tied up, we sail out in awkward, disjointed lines to mine the sea for data. Drunken sea-legged walks down musty gray painted corridors at 0300, coffee ingested, boots and vest on, you stagger out to the deck, tether yourself to standpipes during high seas, push out a 2,000-pound rosette of racked 50-liter niskins on a hydraulic cable, swinging over the workdeck and lowering gently into the sea, like the corpse of a loved one floated out into the Ganges. Curtains of inquisitive squid dart like frantic ghosts left and right in the spotlights. 100 meters down in the impossibly clear water, you can still see the rosette. The CTD transmits secrets of salinity, pressure, and temperature as it sinks down a mile or so over the next 4 hours, trapping giant gulps of water at chosen depths, finally raised up to the workdeck, streaming sunlight and tendrils of water later that afternoon. Steel box container lab on deck houses special experiments, sequesters radioactive tracers. Zombie students and scientists hover over laptops and labs inside the main cabin. Buckets of saltines and ginger ale keep us going. Ice cream is pretty much the only treat. Giant sediment crabs, benthic bear traps, hurled to the seafloor, snap shut upon impact, somehow gently bite into the soft gray mud and bring up its secrets. The entire ship will be coated with salt when we return 2 weeks later, satiated, ready to pour over our treasures and find out what stories the sea has to tell. Thanks. Thank you. Thanks for getting your associate's degree in chemical oceanography. And I'm opening this up so I can see the chat, and I'm happy to answer Can everyone hear Sarah speaking? Hopefully people said yes.
Yes.
Good, good, good. Awesome. So that was very speedy and I skipped over some of the long sciencey parts, but hopefully that gave you an idea of what it's like to be a chemical oceanographer, and not everyone's Jacques Cousteau, and not everyone dives, but all of the science is important. All science is important to kids. There's a lot of opportunities for kids to go out and do this kind of science. It can be lucrative, especially if you're working on the oil. I knew the crew, for instance, that found the Deepwater Horizon oil spill. That was the same boat I just wrote about there. And it was just tootling along in the Gulf of Mexico and happened to be measuring organic compounds in the middle of the ocean. And all of a sudden, there's this giant plug of oil. They discovered that giant leaking thing, which was not announced. Scientists found it and alarmed, let everyone know that there was this fire occurring, that oil was going throughout the entire ocean. That was just in the right place at the right time, looking at the right thing. But any other questions? Yeah, go ahead, Sue.
Question.
Yeah.
You studied lead and CFCs as success stories, but even before we were worried about CFCs, remember way back when all we were talking about was acid rain.
Yes.
What's the problem with acid
You're
rain?
so good. It's like I planted you in the audience. Yeah. Acid rain actually has improved greatly. And that was another thing that scientists were doing, especially in New England. So Hubbard Brook is one of the founding field stations where acid rain was discovered. So acid rain was occurring mainly through car exhaust, NOx, nitrogen oxides with an X means it can be 1, 2, or 3 molecules attached. But when we had poorly burning cars with diesel fumes that were not 100% combusted, so not with carburetors, not with secondary, turbos, when we were releasing all of this material into the atmosphere, that was turning the upper atmosphere acidic. So you're creating this nitrous oxide acids that were then raining down. This is the, nitrogen's 15 element, pretty good size, a little bigger than carbon. And so it was falling down into all of our rivers, and it changed the pH of all of our rivers drastically. Now, a normal river is going to be 5.5 to 6 pH. It's not 7 pH. Almost nothing in the world is 7. But it was going down to 4.2, 4.3. So we were knocking out macroinvertebrates. We were killing fish. People could still drink the water, but it was really a problem. And immediately people started understanding what the source was and started throttling back on engines and changing combustion. And capping all the scrubbers. When we were kids, you'd see these big industrial plants were just spewing just nonstop. People thought, and they still do, that the ocean is so vast that there's no way we can mess it up. We thought the atmosphere was so vast, there's no way we could mess it up. And we thought the whole planet was so vast that no matter how much we polluted, we could never mess it up. What's really alarming is we've changed the pH in the ocean by 0.75 pH units. That is that's a huge amount. That's all from carbon dioxide, but we've at least fixed acid rain. So the reason that that's gone away is because we've removed all the sources of that. And a couple of those pictures I showed earlier was showing how we track the nitrous oxide. And so if I was wanting to measure if a chemical scrubber was working, let's say in Bedloe Park in California, I would set out measurement devices all the way around it to look for nitrogen coming from the rain and looking for this nitrous oxide. So there's ways that we can make sure people are doing the right thing. But that's a really good success story that people immediately panicked, as they should, and said, we can't be killing all these fish. And there's huge fish kills. I'm sure you guys might remember rivers were catching on fire. The level of pollution when we were children was unbelievable. Going to the New York Harbor actually was very interesting to see, because I'd sampled New York Harbor before then, and it's seen like 10 years before the World Trade Center. And it was just a black mud, just like we were talking about, David, just all dead mud, all anoxic, no clams, no mussels, nothing was alive in it. Back when, 15, 11 years later with the World Trade Center, the mussels and clams were coming back. Same in Boston Harbor. When I first did a sampling in Boston Harbor, it was horrible. You would take a step in there and your arm would start burning, because it was so anoxic, and anoxic mud is very acidic. So, you're just like, I think my entire skin's coming off. Now that's all recovering by bringing in clams and by stopping the pollution. So you can't do just one and not the other. You can't bring something to clean something up and keep polluting. So that's the big concern with climate change is that we've got so much carbon dioxide in the atmosphere, it's going to take 200 years for it to recover. We have to not only bring in ways to remove that carbon, like through phytoplankton, there's a million ways to remove carbon from the atmosphere, but we have to stop the input. And fortunately, with acid rain, we did both. So that's a great question. Thank you for asking me. When Doug LaFollette speaks on April 22nd, he lived each bit of that policy change. All of the changes throughout all of America, people on either side cared about the environment. And they still do. I think people still do. I think that people really want to make a difference. It's a good question. Anything else? Yeah.
Another question, you talked about sort of the half-life of certain iodine, and then there's other stuff like the silica, fiberglass. I don't know enough about gypsum to comment on it, but when that stuff's in New York Harbor, is it just becoming somebody's future sediment core, or is there a process that turns that chemically or biologically into something less noxious?
That's a really great question. Fortunately, the iodine 131 will decay.
Right.
So anything radioactive, so that marker is going to get dumped on by clean sediment. And as I take a core 10 years from now, 20 years from now, 100 years, 1,000 years, that'll be the World Trade Center line. Will not go away. You'll always be able to find, it'll freak people out. In 100, 200 years, they'll take a sediment core and go, why is all this burnt balls of copper and zinc here? Why are we seeing gypsum in the middle of a harbor? So that is going to be just like the KT boundary or the bomb fallout. It's going to be permanently recorded in the sediment, but it's going to be capped. We could do a whole nother talk. Some contaminants can migrate out. One thing that was interesting in Galveston Bay is I actually did research following shrimp draggers. And so sediment would pull down all this copper. And once again, Houston Ship Channel, one of the most contaminated bodies of water in the country, is Galveston Bay. So the sediments would take the copper and the zinc and all this horrible stuff and hold on to it until a shrimp dragger came along, and then it would resuspend the sediment into the water column, and it would shed some of these metals, which then the shrimp would take up, and then they drop back down. It was very quick, episodic, but enough to actually change any kind of ground fish. So we can measure it in flounder, sole, any kind of ground level fish. And it's not something unless you're thinking about it and saying what process could release this evil stuff. I think I've locked it up and I haven't. That's the big problem with carbon is we keep thinking of great ways to lock up carbon, but we have to think of ways to lock it up permanently. So, but yes, you're correct. You will be able to see that calcium and strontium will be like a flashing red light to any sedimentologist, and that looks at the hues. And what we were looking, we did the over by the battery. We went around to the west end. We went all over, and you could find different areas where more sediment was collected than others. So that's why we would, if there was something like a big accident, like an oil spill in New York Harbor or of the subway, where would we go dredge? So in some cases you'd want to dredge, but you might recall going all the way back to the battery contamination PCBs in the northern, they actually decided to cap that instead of dredge it. Certain things like asbestos and PCBs are worse if you try to pull it out. So they actually would concrete over parts of rivers and cover up the sediment and say it's done. Just,
I have one quick question.
yeah.
Did maybe I heard you wrong, did you say most rivers are 5.6 pH level?
Yeah, so rainwater is 4.5 to about 5.5. Most rivers are closer to rainwater. Groundwater is even more acidic. Rivers can get more alkaline if there's more phytoplankton.
Well, 7 being neutral. The pH
7's
level-
very rare.
Well, we had how about salt rivers, like St. George?
Salt rivers are, the ocean is 8.3 pH. 8.3. 8.3. All of the ocean before we messed with it was 8.32. And actually, chemical oceanographers know it as 8.32167. I mean, we knew it out to, like pi. Yeah. But what's bad is we put so much CO2 in the atmosphere. So one of the things we use in our classes is a soda stream. I actually have, we inject CO2 into water and you can see the drop in pH immediately. We put so much CO2 into the ocean, we've dropped it permanently 0.75 pH units.
Wow, I know Sarah glad, she works out down in Scotland.
Uh-huh.
And I don't,
Haven't met her
she
yet.
did, pH levels in St. George River in a couple of places. One of them was like 7.2 in November.
Yeah.
Well, I was under the impression anything below 7 is acid.
It is.
So, I
But
mean,
fresh water is acid.
so, oh, but so in salt water, I mean, if we get below low, we got clams, lobsters, anything with shellfish, it's just like sticking it in battery acid.
It's not quite that bad. It's not good for them. So it's showing that fresh water, but fresh water is like, if I took a rain bucket right now and put it outside after all this rain and collected that, that's going to measure about 5 to 5.5.
Really?
Just coming through the clouds, just naturally. Rain is acidic. Groundwater is pretty acidic. Groundwater is 4.8 to 5.2. Rainwater can go up to 6, but rainwater is never 7. Yeah, it's
But
just.
the ocean,
The ocean is because of all those wonderful things, carbonates, the whole carbonate cycle. So all of that is there's a whole carbonate cycle that's introducing carbonates buffers into the ocean. So the oceans are well buffered. What's alarming is that we've overcome this giant buffer system. So you can think of a coral reef as dealing not only with higher temperatures, it's ejecting all of its phytoplankton. That's what's called coral reef bleaching, but it's also dissolving. So all three, I actually had 2 or 3,
that's the reason why it's-
yes,
we want to know if it showed the result, the plant is being dissolved.
they can be. And if it's super anoxic is very acidic. So anoxic conditions are acid to begin with. Anoxic without oxygen, any kind of black sulfurous mud is lower pH to begin with. Yeah, because there's no oxygen. The oxygen helps bring along the alkaline. So you have to have oxygen in that carbonate cycle. So, and some anoxic, it's simply just use an oxygen meter. Just an oxygen meter measures it. Huh? Yeah, in fact, what they're doing in Massachusetts, they're sticking them on lobster traps. Because there's they're sticking oxygen meters on lobster traps. Because there's a huge dead zone where lobsters are dying right off the Cape. So when you look at Cape Cod, there's a dead zone right by my ear. Huh? Not terribly. No.
We don't know his budgets.
Yeah, I know. I'm all about little budgets. What was interesting is, so all the other fish can get out of the dead zone. Lobsters are in the trap, they were dying. And so there's a bunch of fishermen that were, and typically the state was actually providing that. And they're simple little devices. You just put on your trap, you pull it up, and you can measure how the oxygen changes. It's interesting to see as you're bringing it up. The seafloor should be in a rocky intertidal area like we are, it should be pretty well oxygenated. You wouldn't, you're going to have drops in oxygen, but it shouldn't be terrible. But if you have, most of the dead zones are created by fertilizers. So people over fertilize their lawns, all that food goes right into the ocean. It creates this huge phytoplankton bloom, typically in spring. And then that phytoplankton dies and is consumed by bacteria and the oxygen plummets. So
We seen that in our good, I seen them algae so heavy. And I called the state biologist down, she came down, and it would literally not float with the tide come in. And I see the little tiny seed clams and big clams pushing themselves literally out of the mud because they can't breathe.
yeah.
And then they become green crab, sea dog food.
Right.
I've actually seen this in St. George.
They're actually going to be, putting those oxygen, meters, on main lobster traps this year.
They should be, yeah.
Yeah.
Yeah, there's a bunch of money that I helped advocate for a long time ago for a variety of reasons. That should be attached to a large omnibus spending bill that's going to the states. And a lot of that should become, what scientists call ferries and any kind of shipping, groups, and all fishermen are opportunistic samplers. So, even on a ferry, we would shoot CTDs, which are conductivity, temperature, depth finders over the side as we're going on transects. So it always makes sense to take advantage of all these people being out in the water and help supplement. On Nantucket, I used a scallop fishing boat was my primary research boat. So I could hire him year round when he wasn't scalloping to do all the research with me. It made way more sense than buying a boat, for instance. And I skipped all the exciting iodine plutonium stuff, so you'll have to catch that another day. But hopefully, thank you for sticking in. I know it's some high level, did it make sense? I know I was speaking very quickly. This is literally, that's a PhD level stuff there for you guys. So you guys did a great job of hanging in there, so I appreciate it. Thank you. I need a glass of water. I meant to get water and didn't. Thank you guys for being here on, hope you're still awake and alive. Thanks for joining us.